Welcome, everyone. I'm happy that we are all together today and we are going to have a really interesting 90 minutes. And you're going to make sure that it is interesting. You're welcome to ask questions. You can ask questions by using the Q&A option here. And I'm going to look at it once in a while, say every 10 slides. And I look forward to answering your questions. So here is what you're going to get in this 90 minutes. Remember that this is machine learning and NLP for the beginner. So you're going to get what is machine learning, how does machine learning work, and what's in it for me. The third point, of course, is very important. Okay, so let's get started. You will notice that I have this table of contents slide. You're going to get a copy of this presentation and you're welcome to browse and so on. But I should also warn you that this is not meant to be read like an article. It can be useful as a refresher. And if you're going to use it, if you're browsing, you can find that you can always return to this slide by hitting on table of contents here. Okay. So because we are still warming up, let me waste just a little bit of time with this slide, okay, about me. Okay. So this picture is more or less like what I am right now, except for the quality of the haircut. Okay. So I have 20 plus years of experience in scientific programming, etc., and teaching. Okay. And I'm the founder and CEO of my company, Numeric Insight. And you're going to see a billboard at the bottom of every slide here. And I would also like to draw your attention to the fact that most of the material that you see in this presentation, the graphics and so on, is copyrighted. You're welcome to use it to enhance your understanding, but please keep in mind that it is copyrighted. So what do I do within Numeric Insight? Yes, I'm very fortunate that I get to know about really interesting applications of machine learning. Not just machine learning, but a whole lot of other disciplines having something to do with numbers, numerical analysis, computation, and so on. Okay, that's what I do. I also teach not only for UCSC, that is University of California at Santa Cruz, also for UC Berkeley, and I also teach for companies. I'm currently about to complete a really interesting series for Visa Research. Visa is the credit card company, as you know. So they are, of course, interested in text processing and natural language processing. And some time ago, I think about 1 year ago or so, I completed a series for Walmart Labs. I think you know Walmart Labs is, of course, related to Walmart. And Walmart Labs is a huge e-commerce entity. I also have an upcoming series. Unfortunately, I'm not at liberty to disclose the name of the company here. I'm going to start machine learning for signal processing, which is unusual and unique, if I may say so. Okay. So I've been very fortunate that I have these opportunities to teach and thereby learn more interesting stuff. Okay. So these are all the domains and topics that I have worked on. I'm not going to spend too much time here. And most importantly, because we are doing this under the auspices of UCSC, Silicon Valley. The summer session at UCSC starts very soon. And I've been told that there is a promotion 20% off. So I urge you to take advantage of that, okay, if you're interested. So let's keep going. Oh, I forgot to tell you. I have also worked in the medical device in space for Boston Scientific for a number of years. And before that, I was at the Cleveland Clinic Foundation. So in both the Boston Scientific Corporation and the Cleveland Clinic Foundation, I was so fortunate to find opportunities to work on medical imaging and machine learning applied to medical imaging. I'm really grateful to these opportunities. So let's keep moving along. So as I promised you, the first slide is, what is machine learning? Okay. So machine learning is the science of creating functioning computer-based systems without explicit predetermined specifications. Okay. Explicit predetermined specifications. Okay. What does that really mean? So I'm going to compare and contrast traditional computation with machine learning. So with traditional computation, you have to study a body of knowledge, deep study very often, and then you can use that knowledge to build models based on that domain, say physics or chemistry, metallurgy, material science, whatever it might be. And then you can craft an algorithm based on that model. And then that algorithm is going to come with some performance guarantee because it's thoroughly grounded in the physics or chemistry or biology. We say thoroughly grounded, but it is only grounded insofar as the models capture reality. Okay. So this is traditional computation. What about machine learning? With machine learning, you start with data acquisition. Okay. And you create a training set. What does a training set mean? Okay, we'll come to that soon. And learning takes place. Machine learning takes place. And what you end up with is a black box machine. Okay. In order to create that black box machine, you have a tunable model. Okay. This tunable model is going to learn something from the training set and create the black box machine. So it might seem, if you look at this, that this is totally divorced from the domain knowledge. That is true, but not entirely true. Some very successful machine learning systems do use domain knowledge. Okay, so domain knowledge can actually inform your tunable model. Okay, so it makes it even better. Okay, so I suspect that if I show you these two blocks, traditional computation and machine learning, it's not making a whole lot of sense to you. Okay, in fact, these two summaries of traditional computation and machine learning really make sense if you already know what machine learning is. Okay, so that's a bit of a catch-22 here. But however, I think it will become clear as we keep going along. Okay, so I'm quite sure that when considering what is machine learning, you're all aware that you must have used machine learning today, perhaps without your realizing that you are doing so. Okay, how is that? Okay, I'll let you think about it for a few minutes. Okay, so I want to introduce you to a real life example of machine learning that is going to make all these admittedly abstract blocks a little more concrete. Okay, so let us take a look at a real life machine learning example from the banking industry. Okay, now here is a machine learning problem. Okay, Alice works in a bank that actively sells loans. She needs to meet her daily sales quota. Okay. There's not a very pleasant situation to be in, but that's how it is. Okay. She has basic information on Bob, including his phone number. Now, Bob is a customer of the bank. I think now you're understanding that Alice is the type of person who calls you just when you're about to sit and have dinner. Okay. So she calls you and asks you, hey, we have got this great home equity line of credit, and you are such a great customer. So I think you'll be really benefited by this. So she tries to sell loan, a home equity line of credit, for example. Okay. So she is worried, before she actually presses some buttons to start talking to Bob, she is worried that she will have to spend 30 minutes talking to Bob with no guarantee of closing any deal. Okay. So should she call Bob or move on to the next potential customer? Okay. So this is the machine learning problem. So I want you to take a look at this data. Okay. I also want to show you the reason why I'm showing you this data is because the solution to this problem is going to depend on this data. Okay. So if you look at this data, every line here is a customer. It represents various features corresponding to a customer. Okay. You have age, job, marital status, education, and so on. Okay. You also see here in this last column, it tells you what happened with that particular customer. Did that customer purchase or did that customer not purchase? When I say purchase, I mean, for example, did customer number 1 sign up for that home equity line of credit? No, they did not. How about customer number 3? Did they sign up for that home equity line of credit? Yes, they did, and so on. Okay. Um, this data actually is publicly available. It has been reported in this publication, and it is also available in certain websites which maintain really interesting and useful data sets. Okay. So you see, if Alice wants to decide whether to call Bob or not, then she has to compare Bob's financial variables against entries in this huge database and compute a prediction. Okay. So this database is historical record. So for every item here, for every entry here, the bank knows what happened. Did that customer buy or not buy? Okay. So this information can be used by Alice to know, is Bob more likely to buy or not? Okay. So she has to use this information in some way. When I say that she has to, I really mean the software has to. After all, Alice is going to be given a piece of software that she can use. We are going to take a look at that in a minute. Okay. But there is another important reason why I'm introducing this problem to you. The reason is this is an excellent opportunity for me to introduce some jargon. Okay. Jargon is a mark of knowledge, right? You can use it to impress your boss. So there's an excuse to introduce some jargon. So here is that piece of that data set that I showed you. Okay. Now, all of these columns are called features. Okay. Age is a feature. Job is a feature. So unemployed is also called a job. Marital status is a feature, and so on. Okay. And you see here, the last column is not a feature, but it's called a class label. Okay. So the word class here, I think it's going to make some sense to you very soon. When I say classifier, it has something to do with finding the class label. Okay, we'll come to that in a second. So this last column is a class label. These are features. And if you take a look at any single customer, okay, so this set of attributes or set of features, if you consider it in the correct order, the order that is given here, that's called a feature vector. Okay. Machine learning depends heavily on the science of vectors. Okay. The science of vectors is called linear algebra. In fact, many of my students, once they're introduced to it, they really get hooked on linear algebra because it's really a workhorse in terms of mathematical techniques. Okay, so many methods in machine learning depend on linear algebra. It's nothing that is too difficult to master at all. Okay, so right now you know the meaning of feature vector, you know the meaning of features, you know the meaning of class label. Okay, so I'm going to skip this, but I have also tried to distinguish between types of features. Okay, let me just skip that for now, but you're welcome to ask me later if you're interested. Okay, so this whole database, which contains past history of customers, is called a training set. Okay, and well, I want to show you the software that is used by the bank, the software that Alice sees just before she makes a decision. Shall I call Bob or shall I skip? Okay, so Bob's fate is decided by this piece of software. Okay, you can see here that Alice has entered, using this interface, Alice has entered Bob's specifications. Okay, so in other words, this is a query that has been built up and the software is making a prediction. No, as in Bob is not going to uh, buy this financial product which is being offered. Okay, now just to give you a sense that this is a real life application which really works. Okay, in fact, I had a role in creating a similar system. Okay, I'll show you, if Alice decides to play with this a little bit and see what happens. Okay, so you can see here, if the job description changes from admin to management, you can see that the prediction changes from no to yes. Okay, this is no, this is yes. Okay, and you can also see here, if this housing status changes from yes to no, you can see again this class label, which is the prediction, is changing from yes to no. Okay, so it is working. I just wanted to show this to you just to give you a sense that yes, there's a lot of um, science under the hood, but ultimately you have an interface or an app which makes it all seem very easy, right? So that's what this is. Okay, now that you know this jargon, okay, the jargon being, you know what features are, you know what a feature vector is, you know what a class label is. Okay, I think I can give you a better definition of machine learning. Okay, a better definition is here. Okay, machine learning allows you to do this. It allows you to feed in a feature vector to this entity called a classifier and get a class label out. So a class label you just saw is something like yes, no, as in purchased, did not purchase. It could be so many other things. It could be male, female. It could be so many things. It could be spam, not spam, when you're talking about email and so on. Okay, these are all called class labels, of course, right? So when we say class label, we are talking about some discrete entities. Okay, it's not a continuous range of numbers, but discrete entities which are qualitative. Okay, so in order to create this classifier, you need a training set and you need a learning algorithm, and that's going to produce that classifier. Okay, so the classifier has to be designed, and once it is designed, you can use it. Okay, now this is known as supervised learning or learning from labeled examples. So why do we say labeled examples? Because in order to create this classifier, you need a whole lot of feature vectors, and you also need the corresponding class labels. Okay, labeled examples. Now, just to make this more concrete, let me just throw a few examples at you. I already said email. Okay, email, most of the time, you will find is automatically classified by your Outlook or Gmail or whatever maybe your email portal. It's going to automatically classify incoming email into spam or not spam. Okay, sometimes entities like Google or Gmail classify it into not just two classes but multiple classes, such as promotional, social, spam, of course, right? And so on. Any of you, if you have Gmail at all, which must be most of you, you must have seen these labels, right? So that's an example of a classifier, of course. Okay, you might also have come across some of these modern cameras are really good. Okay, really old-fashioned cameras used to pose some difficulties in capturing a subject's smile. Okay, because you never know when to press the button. Okay, and when you do press the button, the subject is not smiling. Okay, now modern cameras have a smile detector. Okay, I'm sure you must have come across it. So the software inside the camera is in real time continuously running a classifier, and the classifier is classifying the face or the emotion of the face. It's classifying it as smiling or not smiling, right? So I'm just giving you examples of classifiers so that you understand the meaning of class label a little better. Okay. Now, I also want to tell you that I have told you about supervised learning. Okay. There is something else. Okay. Which is unsupervised learning. Okay. Unsupervised learning or learning without labeled examples takes feature vectors, passes it through a special type of classifier, which is not going to give you any labels. But however, it's going to group all the feature vectors into categories or clusters. Okay, so it's going to say that this bunch of feature vectors are all similar to each other, and they are all different from this other bunch of feature vectors, and that other bunch of feature vectors are all similar within themselves, and so on. Okay, so that is unsupervised learning. Okay, I'm sure this is still kind of abstract. Okay, to I can help you out here. Okay, let's take a look at this example of supervised learning. I'm going to show you this training set. You will see that it has a bunch of shapes. Okay, it has three shapes: triangle, square, and pizza. Okay, so you can imagine that you're going to create a classifier. Okay, and it can take a query and classify that query. Okay. This example, which I am showing you here, it's doing the job correctly, but it's not good really. Why do I say it's not good? I say it's not good, or it's not sufficiently good, because this query exactly appears in the training set. Okay. So in order to answer this query, you don't really need machine learning, right? You might as well just have a lookup table, okay, or matching. Okay, if you can just somehow take this and match it against each of these items till you get a hit, then you got your answer. So it's not really machine learning, right? We want our classifier to be good enough that it can even answer queries that don't appear in the training set, okay, like this or this, okay. And if your classifier is able to do this, then you say that it has very good generalization, okay. To be practically useful, a classifier must have the ability to generalize on learning from examples, okay. I'm just introducing some terms here and there, such as generalization, just to make you more and more comfortable with the entire subject, okay. Now, I think you must have understood that with supervised learning, you teach the system by showing it examples, okay. With unsupervised learning, the situation is like this. You have a whole bunch of data, no class labels, okay. But you want your machine learning algorithm to work on this and come up with this sort of labeling, okay. You will notice here that it has labeled all the triangles with ones, all the squares with twos, and all the pizzas with threes, okay. It has done it automatically. The machine learning algorithm does not really understand that this is a triangle or that this is a square, but it definitely understands that these two are similar and these two are similar, and so on, okay. A human can later, once the algorithm has done this job, a human can examine all the ones, twos, and threes separately and understand the significance that one means triangle, two means square, and so on. So this is something after the fact that a human has to do, okay? So with unsupervised learning, we let the system discover whatever can be learned. Seems very mysterious. How could this work? I promise you, really, that you will be left with some understanding that this is definitely possible. It is plausible. Okay, we'll do that. Okay, I want to leave you with another example of supervised learning. Okay, which is face emotion classification. All right. Let's say you have a large training set containing neutral faces, sad faces, and happy faces. Okay, you can imagine being able to train a classifier. After all, as I told you, something like this is happening within modern cameras, okay? So you should be able to query and come up with the correct class labels when these images are fed into the system, okay? I'm happy to say that many of my former students, uh, at my suggestion, they took this as a class project, and they came up with some really interesting findings and results, okay? To be sure, this is a solved problem. This is not research, but in trying to do this from scratch, really valuable understanding is acquired, okay? And I'm so proud of my students who taught me a lot actually by their doing this project. Some of the insights that they uncovered were new to me actually, okay? I want to show you another example now of unsupervised learning. Okay, so here it is. What, I have committed a sin here. We should never show, a table containing numbers like this in any PowerPoint. Okay, it makes people really bored. But I want to tell you that this is truly interesting. Okay, what is this? This is data that is generated by an e-commerce website. Okay, so every you can see here, every row here represents a customer. Okay, I'll explain this to you. Every row here is a customer, and there are thousands, tens of thousands, in fact hundreds of thousands of customers. Okay, so each customer is described using these numbers, right? And I told you a few minutes ago, um, what do we call those numbers? I don't know if there's a good way for you to respond. Um, well, I'm trying to look at the Q&A feed here. It's okay. Let's let that go. You already understand that these are all features, right? These are all features. What do I mean by recency, frequency, and monetary value? Monetary. This is a very commonly used marketing model. Okay. Recency refers to how recently did a customer buy something. If you're thinking about Amazon, for example, how recently did this customer buy from Amazon? Frequency refers to how frequently does that customer buy from Amazon? Monetary refers to how much money did they spend. Okay, but you will notice here you have 3 recency columns, 3 frequency columns, and 3 monetary columns. What does that mean? That really means that there are 3 departments within that website, within that e-commerce entity. There are 3 departments. They could be books, electronics, and apparel, for example. Okay, so this 4 says something about how recently did that customer buy books? How recently did that customer buy electronics, and so on? Okay, so we've got all this data. Now, here's the interesting thing. Every e-commerce entity, in order to stay in business and be of benefit to us, it has to make a profit. And so it always has to think about, how can I maximize my profit? How can I really extract the most that I can out of my customers without annoying them? Okay, we have to keep them happy, but yet we have to encourage them to part with their money, right? So it's a very delicate balancing act. And in thinking about this, this has been known for a long time, well before machine learning came on the scene. It is always good to group similar customers together. If you group similar customers together, then you can give them some customized and special treatment. Okay, for example, you see here, there are some customers who have negative numbers here against this monetary, right? These negative numbers denote returns, which is bad for the company, right? The company doesn't want you to return stuff, and they don't want to have to refund your money, right? So there might be a bunch of customers who are always returning stuff. Okay, so this e-commerce entity wants to treat them differently from other customers who never return stuff. Okay, so what can they do? If they identify a bunch of customers who are otherwise good, they buy high value stuff, but they tend to return stuff, then they can do things like uh, they can shorten the return window, for example. They can say, yes, you're welcome to return stuff, but you have to do so within 1 week or so on. Or if there is another bunch of customers that has been identified somehow who are very, very good and worth promoting, they can be given a discount. Say, you have been such a loyal customer. Here is some $25 for you to spend and so on. Okay. So there are all these possibilities. So the upshot here is it's of immense value to find groupings of similar customers. Okay. And of course that can be done. And I want to show this to you. See, this is a representation of all the data. Okay. This is a visualization. And let's not worry too much about how that table, which I showed you on the previous slide, is converted to this picture where every customer is shown as a dot. Okay. But whatever it is, you can see that it is still a mess. You have some vague idea that, yes, I think I see some groupings there as it is going round and round, but you can't really see it well. Okay. But on the other hand, if you use a machine learning algorithm called Kmeans clustering, which actually we are going to go over later, okay? At least qualitatively, we'll go over it. You will see that it becomes very obvious, okay? The algorithm has really colored each point, okay? Based on its grouping, okay? It has automatically come up with these colors. So once this is done, the company can always go back and pick out all the green customers and give them some type of treatment, and pick out all the brown customers and give them some other type of treatment, and so on, right? So this is what you can do with it in order to maximize the bottom line and keep all the customers happy, right? So we'll talk more about this later, but just to make this whole idea about what is machine learning a little more concrete, I want to contrast machine learning with something that is not machine learning. See, after all, you have computation. People have been computing for, forever, really. Okay. Computation is nothing new, but machine learning is relatively new. Okay. So if you think about image processing, traditionally image processing is not considered to be machine learning. What can you do with image processing? You can take a picture which looks like this and then get this picture out of it. Okay. This is image processing. I think you are guessing right. This is my wife and this is my daughter. Okay. Now I want to show you machine learning can draw a box around the faces. Okay. The faces can be recognized. This is what most modern cameras do. I already told you about this. And it can also analyze the sentiment in the face. I already told you about this. But I wanted to reiterate this in this particular context, because with photographs, you can do image processing. That is not machine learning. With photographs, you can do machine learning. And with machine learning, you can do all of this stuff. So as you can see, machine learning really makes the camera smart. It makes it seem intelligent, right? Qualitatively. So see, till now I have talked about machine learning and not machine learning, okay? So this kind of begs the question, could there be applications where you can apply machine learning and some other applications where you're better off just sticking with classical computation? Okay. The answer is yes, really. Okay. When to use machine learning versus other things, versus other computational methods. Okay. You use machine learning when traditional engineering or scientific methodology is not applicable or is impractical. Okay. So you use machine learning when a large amount of data can be collected with reasonable effort. You can also use machine learning when a black box solution is acceptable. Okay. What do we mean by black box solution is acceptable? It means you're going to use that machine learning solution and you're going to get an answer. And by experience, you might be able to show, by actual experimentation, you may be able to show that it works wonderfully, but you can't really explain how is it working. Okay. So if this camera is able to detect this smile, can you tell me what is it doing actually to uh, detect that smile? There may be no answer to that question. Okay. So that's what we mean when we say the black box solution. Okay. When it is acceptable, very good. When it is not acceptable, then you cannot use machine learning. A prime example of this would be in the medical device space. There are so many medical devices which in prototype mode, okay, on the tabletop or in research mode, do wonderful things, like might be able to do much better than actual doctors at diagnosing some diseases. Okay. But why can it not be used really in real life? It cannot be used because it's a black box. Okay. It's a black box and there are no guarantees about when it may not work, when it may provide misleading results. And the reason is because you cannot really explain how it works. Okay. So that's an example of a situation where a black box solution is not acceptable. Okay. Now, you can also use machine learning when the system being learned is stationary for a sufficiently long period of time. There's not a serious constraint, but it is easiest to apply machine learning when you have a stable system which is not changing all the time. If you have a system which is slowly changing, you can still use machine learning. Okay. In fact, that's called online learning, where uh, the machine learning solution can track the changes in the system and constantly keep retuning itself. Okay. That's possible as well. Now, I have told you about supervised learning. I've told you about unsupervised learning. Is there anything more really? Actually, yes. But I simply cannot talk too much about this because it's a very deep subject. Okay. And it would, in fact, not only take the whole evening, it can take several evenings. Okay. There are whole lecture series on this topic called reinforcement learning. And very often you hear about three subdisciplines within machine learning: supervised, unsupervised, and reinforcement. Okay. But it's safe to say that the overwhelming majority of applications use supervised learning. But anyway, what is reinforcement learning? Reinforcement learning is all about having an agent within an environment. Okay, you have an agent inside an environment, and this agent can sense the environment. Okay, it gets some information from the environment, and the agent can try to change the environment. Okay, it can do some action to change the environment. And when that action happens, a reward may be offered to the agent, a reward or a punishment, actually. Okay, so you get a reward, which may be positive or negative, let's say. So this goes on for several iterations. Okay, the agent tries its best to get the maximum reward. Okay, so this is very abstract, but I just wanted to share this with you, just to tell you that there are so many applications where reinforcement learning is used. Typically where the environment is totally uh, novel. It's new. It is unexplored territory. It could be the surface of Mars. I'm not kidding, actually. The Mars rovers definitely used some form of reinforcement learning. Okay. Self-driving cars. Yes, of course, they use reinforcement learning because the roadscape is always novel, right? So I have to leave it here. It's very exciting and interesting. I should tell you that. Okay. So with applications in robotics, logistics, trading, and so on. Okay. So I think we have finished with the first part of this evening's talk. Okay. Which was what is machine learning? I hope I have left you with a good sense of it. Now, before I jump to how does machine learning work? Can we at all hope to understand it within 1 hour? Yes, we can. But before that, I would like to look at the Q&A and just try to see if um, well, I'll just take a quick look at the questions. Very interesting questions. Okay. So this is a question from Ajit. Thank you very much for this question. So the question is, part of the problem with machine learning is the infrastructure that is needed. Will you be talking about infrastructure challenges? The short answer to this question is no. Although it's a very important topic, I'm not going to be talking about it because, in my opinion, there are various aspects of machine learning that um, prospective students or practitioners find difficult. Okay, so I would like to concentrate on those. Those have something to do with the absolute basics of machine learning. How does it work, and so on. Okay. Um, so Ajit also asks, how do you eliminate bias? If the original decisions were biased, wouldn't the model learn the bias? Absolutely, yes. And there have been famous examples of the machine learning model being biased. Okay. Facebook got into trouble because of that, if I recall. Yes, we have to understand that all of the intelligence in a machine learning application came from the data. Okay, it's mainly the data. The person who is designing the machine learning algorithm has the ability to tweak things a little bit. Okay, but most of the time, you may not know which direction to tweak it. So you have to depend on the data. So all that the machine learning application can do is extrapolate based on the data. This is by and large true, but there is research constantly to uh, try to detect bias and try to correct for it in some fashion. This is an interesting question. Thank you, Ajit. And so June Harton asks, is feature a term in machine learning? Yes, feature is a term. You can also say attribute. You can say variable, attribute, feature. Okay. Column, yes, column, yes. It's a column as well. Okay. Um, so I'm not sure what 5500 balance is. Sylvia asks what is 5500 balance. I'm not sure what that is. Um, what are the odd numbers at the bottom? -5, 7, 9. So I'm not sure if we are talking about the stuff that I showed you a few slides ago. Let's go to the table of contents and so not sure where it is. This one. -5, 7, and 9. What are the odd numbers at the bottom? I don't see odd numbers here. I'm not quite sure how to answer this, but you are welcome to um, follow up with me and ask this question, perhaps offline if you like. Okay. Can you please show the jargon diagram again? Well, this is a question from June. Not only can I show you the jargon diagram again, I'm going to give you the entire presentation anyway. So you're welcome to it. All right. So there are so many interesting questions here. Now let us see. Here's an interesting question. On slide 11, what if there is another dimension that is independent of shape? Okay, so we are talking about slide 11 here. Okay, what if there is another dimension that is independent of shape? Of course, if that information on color, for example, is available to the classifier, it is going to mislead the classifier. Okay, remember, the classifier does not have any intelligence in the way that you and I have intelligence. So it is up to the designer of the algorithm to make sure that the correct features are selected. Okay, so how do you decide? Ajit has also asked the question, how do you decide which features to use to train the model? Okay, well, so to a large extent, you cannot build a machine learning algorithm without having domain knowledge. So if you have domain knowledge, you're going to know that you have to include all the relevant features. Okay. Machine learning can help you by tolerating the existence of irrelevant features. If the features happen to be irrelevant, in most cases, the learning algorithm can ignore those features, but it cannot, it doesn't have any consciousness to add a feature unless you tell it to add a feature. Okay, so we cannot decide which features to use, but however, this is done frequently in practice. If you believe that these 1,000 features may be important, you can start with those 1,000 features and go through cycles of what is called feature selection and boil that down to a shorter list of important features and work with that smaller set moving forward. That's possible. Okay. So Amir has asked, is Python required to understand machine learning? The very short answer is no, you don't have to know Python. But an equally valid longer answer is, if you don't want to miss the bus, you better learn Python. And here is the good news. It's extremely easy. It's extremely easy to learn Python. And in fact, if you go to the enrollment page, I think it does give you some pointers. Okay, it does help you get started. It's extremely easy, so there's nothing to fear there. And where do you recommend finding more resources on reinforcement learning? I will say really the first step would be start with Wikipedia, start with Quora, and take it from there. And I can also tell you that there is a really extremely accomplished researcher who writes on Quora. His name is Sridhar Mahadevan. I forget really what university he teaches at. He's a researcher. So if you start looking for reinforcement learning on Quora, sooner or later you will come across this researcher. His name is Sridhar Mahadevan. Okay, so if you follow his writings and blogs, you're going to get a lot of resources on reinforcement learning. Okay. Next, I think I should keep moving along. Okay, so how about this? These questions are so interesting that I don't want to rush through it, but we have 1 hour left. Okay. And we do have quite a bit of material to cover. So why don't we do this? Let us keep going and I'll come back to this. Okay. And it is also likely that as we keep going, some of these questions might get answered automatically. Okay. So let's do that. So where were we? Let me just quickly go back here. Okay. So now we are trying to understand how machine learning works. And in fact, I can take a look at the poll. Monica, if you can help me get the poll back.
Yes.
Poll.
Would you like me to share the results from earlier?
Yes, please. I appreciate it. Could you please?
Yes.
Okay, so if I take a look at this, I am not sure if you are able to see the poll on the screen, but
all attendees can see these results and the
very
percentages.
good, very good. Okay, so I see that the most important reason that you find it difficult, you have found it difficult to start applying machine learning is because you have not found a good opportunity. Okay, so when we say found a good opportunity, it could mean anything. It could mean that you are employed, but within your company there is no good opportunity, or it could mean that you are in the market for a good job which will give you that opportunity. So the good news is machine learning continues to be really a sought after skill in the job market. Okay, and we are evenly divided between you thinking that it needs a lot of background in math, you thinking that it needs a lot of programming experience, right? And you thinking that you're not found good resources. Okay, so I hope you realize that at least this bit about finding good resources, that's quite easy to remedy. Okay, in fact, you have taken the first step by being in this webinar already. Okay, and I do hope that between me and my colleagues who teach so many other uh, related topics, um, you're going to find a lot of good resources. And regarding math, I think I am about to convince you that if you just have common sense, and you should not be afraid of numbers, okay? But you do not require any deep mathematical ability. You can understand how these algorithms work and how you can make them do what you want, okay? So let's get started with this, okay? This is an insightful, I hope, this is an insightful example, but it is very silly. I warn you, really, okay? So you just consider this. An airport scanner records a person's height as 67 inches. Is that person male or female? What? This seems idiotic to ask such a question. Okay. How can anybody figure out based on height alone if the person is male or female? Okay. So how do you go about answering such a question even? Okay. Here is one possibility. Okay. You gather a large number of 67-inch individuals from the general population. And when we say general population, we mean the population that might ever walk through an airport scanner. Okay. And you just count the number of females and the number of males. Okay. Count the number of women and count the number of men. I'm using the term females and males in an entirely technical term. So if you'll forgive me, once you count the number of females and males, you just say that that person who just walked through is female if F is greater than M, or that person is male if M is greater than F. It seems so silly, okay? But this is all you can do. This is the best you can do, really. If that is all the information you're given, this is the best you can do, okay? So we can make this seems very trivial, but we can make it sound scientific, okay, by doing a refinement. And we can say the probability of that queried individual being female is this, and the probability of the queried individual being male is this. I think this is easy to understand, right? Because F and M are just counts, that's all. This is the total number of 67-inch individuals, out of which so many are female and so many are male. So these are two probabilities, right? And of course, you can just go with comparing F and M, okay? Or you can go with comparing these two probabilities. You have these two probabilities. You see which of these is bigger than the other, okay? Doing this has some advantages. When I say doing this, I mean doing comparison of probabilities has some advantages, because if the two probabilities are too close, you can say, I don't know, I don't want to guess, right? You can do that. So here's a follow-up question. Can we design a classifier to recognize the gender given the height, whatever the height might be, okay? So here, we are not just saying 67 inches. We are saying the height can be anything, but can we just still do this? How do we represent data showing the heights of males and females in a general population? How do we do it? And actually, if I ask you this question, some image must be coming into your mind. If I ask you the question, how do you represent data showing heights, males and females, in a general population? In your mind, some picture must be coming, right? So try your best to get some picture, and you can see the answer in the next slide, of course. I think many of you must have got it already, okay? So this is not just a textbook exercise. Actual airport scanners definitely do all of this, not merely record the height, but they record a whole bunch of measurements, including weight. And yes, they do actually determine if the person is male or female, or at least they try to find the probability of being male, find the probability of being female. And that information is matched with the information on the passport, okay? And well, and so on and so on. So it's real life, really, except that we are only thinking about a very small slice of that entire complex application, okay? So what is that graphic that you're getting in your mind when I ask you this question? Well, how about this, okay? This shows you a summary of that data, okay? A pair of histograms actually can be used to create a classifier, okay? How does this work? Well, if you have a query, and in this case, a query is nothing but a height, okay? If you have a query, all you need to do is just go to that query on this horizontal axis. You have to go to that query, and you're going to be able to read off the heights, okay? Total number of females and males having that height. And that will help allow you to compute the two probabilities. And you will be able to say whether the person is female or male. And you will also be able to quote this certainty, okay? This is a movie, by the way, just to help you better understand this. I'm just playing it. I hope you can see it. I hope there is no lag, but you can see that when this cursor moves to the right, the probability of male is 100%, right? And when that cursor was at the extreme left, the probability of female was 100%, right? I think you understand this very well. Now, I'm going to ask you to make a big mental leap. If you have understood this part about, you can build a classifier simply by putting together two histograms. Okay. And how do you get these histograms? Yes, you get this histogram or this pair of histograms um, simply by looking at data. Okay. Uh, excuse me. Well, we have 20 minutes left for the webinar. Okay. That's good. I just got a gentle reminder. That's no problem. Thank you for that reminder. So I want you to be prepared to take a mental leap here. Okay. What I'm asking you to do is understand that these two histograms don't really have to be histograms. You can get essentially the same information if you replace the histogram with mathematical models. Okay. Why do we want to do this? Many, many reasons. Okay. One really important reason is that these mathematical models are smooth curves. They might be very robust. When we say robust, what we mean is even if you have less data, it's not going to change things, or it'll change things very slightly. But if you insist on using histograms, you might get totally wrong results. But if you use mathematical models based on that same data, you get much better results. Okay. You can understand this because you can imagine that, let's say a lot of the data is lost, then these histograms will start looking very bad. They will no longer look like these two mountains. Okay. But these two curves, these bold curves, will continue to look like what they are now. Okay. Because these two curves depend only on the mean and standard deviation of the data. They do not depend on any individual measurements at all. Okay. So you can do this still here. Okay. You don't need histograms because you have managed to replace those histograms with mathematical models. And what exactly do we mean by mathematical models? I'll tell you. We mean this. All we mean is that these curves are described using these formulas. Okay. And I'm not sure, but these factors, these terms in the round brackets may seem familiar to some of you. Okay. But whatever it is, there are some formulas. Okay. This pink curve depends only on three things. It depends on the total number of females. It depends on the standard deviation of females. It depends on the mean of females. When I say mean of females, I mean female heights. Okay. And so also this male, total number of males, standard deviation of male heights, and mean of male heights. Okay. Those are the only things that these two curves depend on. And these are much better really. And armed with this, actually, I'll skip the next slide, but I can come back to it later if we have time. I'll just go over this. So you see, whatever I'm showing you here is extremely similar to the formulas that I showed you on the histograms. Okay, I'll show it to you again just in case. See histogram. Okay, take a look at this. So here I say something divided by something plus something, right? So all of that stuff really is nothing but what you're seeing here. Okay, this is something on the top, something plus something on the bottom, right? So it is possible to think of this. Okay, again, this seems familiar to you. I can't go too much in detail, but these are the types of things that you get used to when I introduce carefully crafted examples in the actual course that I teach. Okay, so you will realize that there is nothing to fear if you see something like this. You will not only realize that there is nothing to fear, but you will even be writing code which does all these things, right? So what you see here is going to get you for any query X, it's going to get you the probability of getting a female or the probability of getting a male given that query, right? So this thing, which is simply a ratio, is a probability, exactly what you saw on the histogram. The only difference is when I showed you the histogram for the first time, this was one number, this was one number, and this was also one number. Okay. Now I'm breaking up each of those numbers into two parts, right? That's the only difference. It is possible to write this exact same thing in a different way. You will understand why I'm trying to take you through this process. It is just to make all these things that you see in textbooks meaningful, a little more meaningful, right? So what I'm showing you here is nothing but the top thing that I'm showing you here. There is no difference at all, essentially, between what I'm showing you on the top and what I'm showing you on the bottom here, okay? The only difference is symbolism, that's all. Instead of writing F and M, I'm calling this omega 1 and omega 2, okay? And I'm generalizing further by just writing omega I and saying I can be either 1 or 2, right? And this denominator here, I'm just writing it as the sigma, okay? Sigma with two terms, okay? So I hope you are with me so far. All I'm trying to show you is that when a machine learning application is trying to do some classification, it has to compute probabilities internally. And computing probabilities actually reduces to forming ratios of some counts, right? And that's exactly what we are doing here. There's a numerator and a denominator counts ratio and so on, okay? I also want to show you that um, we have talked about two classes. There is nothing to prevent us from thinking about three classes. Given a height, we should be able to classify, is this person a male, female, or a child? It should be possible to do that. In fact, the formula to do that is so similar to what you saw before, okay? It is just this. This tells you the probability of that measurement being in class omega I, okay, whatever omega I might be, right? And if you have so many of these classes, it's just a question of computing the probability for each of those classes and then just going with the highest probability, okay? It's just a matter of that. So I hope you are getting a sense of how does a machine learning algorithm work? How does a machine learning system work, okay? So we'll keep moving along. See, this is a step beyond this. So till now, I'm talking about computing probabilities using just one feature, okay? I think you can easily understand that instead of one feature, if you're allowed to measure a whole bunch of features, more information is better. And so you should be able to do the classification much better. Surely the formulas are going to become more complex, okay? The formulas such as the one I showed you here, okay? This is for a single feature. There is a similar formula which only looks slightly more complex than this, which can be used for many features, okay? And the whole thing still works, okay? Even if you use that. So it ultimately boils down to this. And I must really compliment you if you're still with me now, okay? Now, I'm going to skip through a couple of slides. I want to show you this, okay? If you start looking at textbooks, you're going to come across this stuff, okay? I hope I have left you with some sense that a formula such as this, okay, if it is explained carefully in a step-by-step fashion, is still comprehensible. Okay, that's the message that I'm trying to project here. After all, you already understood that, oh, this has something to do with histograms, and I know a lot. I really know histograms, and I know how to compute probability using a pair of histograms. Easy. Numerator, denominator. The denominator has a sum of various things. Yes, you see it all here, right? So you see it all here, except the only difference may be that the actual histograms have been replaced with mathematical models. Okay, so there are assumptions and so on. So it works. That's the proof of the pudding here. Okay, you will not only be able to understand this type of stuff, but as we go through classes, um, there are altogether 10 classes in the Introduction to Machine Learning series. You will even find that you can easily understand and apply to your advantage things like this. But actually, I also have to tell you a little bit of good news here. In order to build machine learning algorithms, you don't have to do everything from scratch. Okay, this is very important to understand. So you don't have to actually write programs to implement everything that you are seeing here on this slide. Okay, because there are packages to do that. But I will say this, if you understand all these concepts that go into creating that package, then you will be able to use that package much more effectively. In fact, if you just take a look at any package that is available in scikit-learn, scikit-learn is a very, very important and essential machine learning toolbox. Okay, Python. Okay, if you take a look at many of the modules, you'll find that they have so many options. Okay, and if you try to look at the descriptions of those options, they won't make any sense to you unless you know how that algorithm works. Okay, so you can intelligently set those options only if you know how the algorithm works. And knowing how the algorithm works is going to set you apart from, I'm sorry to say, I come across many practitioners of machine learning who remain clueless, and thereby their applications might only enjoy a modest success. Okay, but that's not you, I'm sure. Okay, so I want to leave you with a little bit of understanding of how does Alice software work. Okay, I showed you Alice and Bob, banking, etc. Right? So let's say take a look at how that works. Does that have anything to do with histograms? Not really. So here is a key idea to understand. Feature vectors are points in multidimensional space. Okay. A lot of problems in machine learning have solutions in geometry. Just like you think about a plane and points in a plane and drawing lines and circles and so on. You can do the same operations in multidimensional space. As I said before, that's the beauty of linear algebra. Okay, so I'm showing you one customer here. Okay, this one customer might represent this point. Okay, I'm just, for simplicity, representing it as a point in two-dimensional space. But keep in mind that it's a point in multidimensional space. This is only for visualization. Okay, so take a look at all these other customers. They are also points, right? They're all points. And you see, there are 10 points here that I'm showing you. Now in the training set, every point also has a known class label, right? So I'm showing you the class label here now, okay? And you can see that the class labels are colored red and green, and the red and green also shows up in these points, okay? So why do I say something about geometry? Yes, because if I consider the entire data set, which may have lots of points like this, okay? Building a classifier reduces to drawing a line And once you draw this line which separates as best as it can the green points from the red points, you see that the problem of solving this machine learning problem reduces to the geometric problem of finding is that customer above that line or below that line. Okay. And that problem can be easily solved using geometry. Okay. You can just find the distance between that customer and that line. And if that distance is positive, then it is one class. If the distance is negative, it is the other class. It's as easy as that. Okay. I just wanted to leave you with this sense. Now, I also introduced you to another problem that was unsupervised. Okay. Recency, frequency, monetary value, you remember? Okay. How does that work? I want you to just get a sense of how that works, right? Because after all, we are talking about how does machine learning work, right? I want to show you this. How does unsupervised learning work? Well, take a look at this unstructured data. This has nothing to do with the marketing data that I showed you earlier, but this is unstructured data, okay? In order to find, let's say my goal is to find clusters. I want to find some number of clusters. Let's say I want to find 5 clusters, okay? How do you do it? You do it by just throwing 5 points in this space randomly, totally randomly, okay? Next, what you see here are the 5 points that I threw just now. Next, what you do is you find the friends of each of these means. By the way, I'm calling these 5 points as means. Why are they called means? You will see, okay? So I'm calling them means. You find the friends of each mean. What do I mean by friends of each mean? I mean this. See, all of these points colored in green are friends of this mean. I say they are friends of this mean because they're closer to this mean than they are to any other mean. Okay, by the same token, all of these points are friends of this orange mean because they're closer to the orange mean than any other mean. Okay, I think now you understand the meaning of friends of each mean. Okay, so we have found the friends of each mean. What do you do next? What you do next is you find the mean of the friends. Okay, you take all these green points and find the mean of the green points. Okay, find the centroid of the green points. And once you find the centroid of the green points, you push this green mean to that centroid. Okay, you see that happen there, right? So you keep doing that. Okay, you keep on doing that, keep on iterating till it doesn't change anymore. Okay, once you're done, your job is finished. Okay, you can see that it has nicely got clustered. Okay, clustered into similar groups. This is how unsupervised learning works. This is one of the simplest and most effective and frequently used algorithms in machine learning. Okay, and that RFM model that I showed you actually was solved using this method. Okay, now what's in it for me? So we have finally come to the last part and we have only 4 minutes left. I hope that Monica will forgive me if I go just slightly over in case you have any questions. I'm not sure, but let's cross that bridge in a few minutes.
The recording will not shut off right at 7, so we can go a little bit over.
Okay, perhaps just 3 or 4 minutes. Depends on the questions, really. Okay. So what's in it for me? I want to show you this picture. So this picture is a collage of company names. I'm so fortunate to have had students who went on to get jobs in all of these companies. I'm just showing you a small subset of all these companies. And they are happy to keep in touch with me. And occasionally they write to me and tell me about the wonderful things that they are doing. Okay. I always find it really good to keep in touch with my past students. And again, I've been fortunate enough to work on projects in those companies or do teaching, customized teaching in those companies as well. Just to give you a sampling, this is what my students do, okay? Lot of real life applications, right? I won't go over it in any more detail, but I just wanted to show you this. What's in it for you? Yes, all this wonderful stuff is in it for you, unless you're already enjoying this. I also want to, in this time that we find ourselves in, talk about machine learning for social good, okay? Google and some other companies have been at the forefront of applying machine learning for social good, okay? I'm not going to spend too much time on this, but you can click on these images to be taken to the websites where you can learn about opportunities to use machine learning in very meaningful projects, okay, to elevate society. So it's not about selling the most amount of merchandise and so on. That's important, perhaps, to stay afloat and thrive, but some things are more important, okay? So I'll urge you to explore these things. And how do you get started with machine learning? Okay. How do you break into the field of machine learning? You should realize that you already know machine learning. I'm sure this is the case because when I talked to you about this histogram classifier, you thought, what? This is so intuitive. I already know this, right? You should allow yourself to wonder how these amazing algorithms work. How does a cell phone uh, know whether I'm smiling or not? Isn't it mysterious? Okay. So attend classes. You can attend classes if you are capable, and I know many are. You can read on your own. Yeah, there is so much of material available. You can absorb and start applying. Make a noise, ask questions. You insist on understandable explanations. At least if you come to my class, I expect you to do all of these things. You're going to fail at programming assignments. You're going to write clunky code, but suddenly you will realize that you know more than you did before, okay? And you will rejoice that you can read and understand the literature, and you can celebrate the authorship of code that does amazing things, okay? This sounds a bit like some inspirational stuff, but I do find it inspiring, okay? So I think I can leave it here. So I'm happy to answer any questions that you may have. We might just overshoot a little bit. It is 7:01 now. I see that there are some questions, but if you'll forgive me, I will take some of the later questions. How machine learning could be used in drug design? Oh, I could talk a lot about this topic, but to answer any question along these lines, how is machine learning used in X, whatever that X may be? You just make Google your friend. And actually, I can tell you one thing. You just look up machine learning on Wikipedia and go to applications. I remember seeing this. You see you see a block containing at least about 100 bullets. Okay, lot of applications, and I'm sure drug design is there. Okay, so if you click on it, you will understand how machine learning can be used in drug design and so on. So I have to be brief. I hope you will forgive me. So is the curve made with the assumption that um, the data is normally distributed? Yes, it is made with that assumption. And I really compliment you for catching me on that. If the data is not normally distributed, what can we do? Yes, there are more complex mathematical models that you can use. Okay. In fact, you can even tailor a mathematical model to fit whatever data you want. So it is possible. But to the extent possible, we should try our best to keep the models based on our assumptions, the models as simple as possible. Okay, so we did that. Is this histogram about adults only? Yes. In fact, I did tell you when I was talking about multi-class classifiers that you can have three overlapping histograms showing females, males, and children as well. Okay. And the theory remains almost the same. Okay. To find the probability, you would have one count in the numerator and three counts in the denominator. That's all. Okay. So that answers that question. How much of machine learning involves statistics? I would like to say that in order to get started and contribute, do useful things, if you know high school level statistics, if you know the meaning of mean, standard deviation, you're good, really. The other concepts that you need to know, um, such as covariance matrix, for example, okay, that's a little more complex, but it's not something beyond you. If somebody explains it to you carefully and in an intuitively appealing way, I'm sure you will follow that. Okay, so the answer to the question, how much of machine learning involves statistics? It is based on statistics, of course. It used to be called statistical pattern recognition, but it doesn't mean that you have to know a whole lot of statistics. And I understand why this question may be asked. Statistics is considered to be very boring, very dry and boring to read and understand. Okay, so I understand that. Can you reduce the input dimensions? Yes, that is really a very um, essential pre-processing step very often. Okay, dimension reduction. There are methods based on linear algebra. There are also methods based on deep learning to reduce the input dimensions. So that is done frequently just to make sure that the data is manageable. Okay, so how can we solve the problem of having too few training data? Are there any known techniques? Yes. So when you say too less training data, you can always use a model to make up for uh, lack of training data. You can do it to a certain extent. And sometimes you may have a lot of training data, but they are not labeled. Labeling may be extremely difficult, time consuming, and expensive. So what can we do? Yes, actually, you can do a whole lot of things, again, using machine learning. In fact, there's an entire subfield called active learning that you can use to your advantage. Okay, so that is that question. And so what programming languages should someone in the field of machine learning know? The best answer I can say is, oh, you learn Python. Okay, and then we will talk. Okay, so if you do not know Python, but if you know some other programming language very well, if you know R or if you know C and so on, you can still do a lot of useful work because there are packages that other people have written which you can take advantage of. Okay, so are clustering algorithms a step before ML or are they ML? I would like to say they are machine learning, clustering algorithms, unsupervised learning, right? Um, so I'm not sure what this means. GPT-2, uh, you're welcome to ask me later because I can take a look at this website that you have linked and see if I can answer this question. Um, okay. How can we use machine learning to decipher system logs so follow-up actions can be triggered? This is a great question. In fact, I've been part of a project where this was precisely what was being sought. And yes, you can use machine logs and you can do a fairly good job even if you don't have a labeled data set. Okay, if you have accumulated logs over a period of time, you can always cluster them and try to make sense out of them. So this is definitely possible. Okay. So I guess I have already taken too much of your time, gone 8 minutes over. So I'll say thank you very, very much. And should you wish to keep in touch with me, you're going to find my email address on the last slide of the presentation that Monica is going to make available to you. Okay. And I know I haven't answered a few of these questions, but I am ever always willing to answer your questions if you send them to me by email. But I think to be fair to the staff at UCSC, I better call it done now. Thank you very much and have a good evening. Bye-bye.